Yes, so I will be presenting work on the Clifford commutant. I will mostly try to give like an intuition via Salvatore and Jens from FU Berlin. And yeah, I start with the basic preliminaries. So we have the Pauli basis, of course, consisting of X, Y, and Z Paulis. And we have n many qubits that we are considering. So we are considering the case with multi-qubits. The Clifford group, I mean, I guess most people here are familiar. But the key insight is that the Clifford group is a subset of all unitaries that map Pauli operators to Pauli operators, but up to a phase. So they can change the sign of the Paulis, but they need to map a Pauli to a Pauli. So when I say commutant, what do I mean? I mean the k-copy commutant of the Clifford group. So if I have a Clifford that I apply, basically on k copies I apply the same Clifford. And then the commutant is just all operators on this n by k many qubits that commute with the unitary. Or to put another way, basically they are invariant under the adjoint action of the tensor power of the Clifford. Now, there's one useful tool here that is called the twirling operator. And it is a channel that essentially just is the process of you choose a random Clifford and then you apply it to your system. And this twirling operator, because the Cliffords form a group, has a very nice property, and that is that it projects basically any operator into the commutant of our group. And in particular, we have, I mean, lots of people have used it, a definition for designs, which is essentially just that the k-order twirling operators of our group matches that of the Haar random group. So then a design is, of course, something that's like statistically indistinguishable from the Haar measure when applied. Now, I will quickly give a reason why you guys should care about the Clifford commutant, because it has actually quite a few use cases where they show up. First of all, I mean, there's general interest. So those two papers as well have already worked on it quite a bit from a more mathematical representation theory background. So just analyzing the structure of it is in itself, I think, quite interesting. The big application that's also been more popular in recent years is property testing, in particular when it comes to Cliffords and stabilizer states. The reason or the key insight why the Clifford commutant pops up is that if you want to test the stabilizer state, having access to some copies of it, the optimal POVM that one can apply needs to live in the commutant. So it suffices to analyze the commutant to kind of determine, to test and learn stabilizer states. Yes. Then also magic state resource theories have quite a lot overlap with this commutant, essentially as well because the Clifford commutant, the elements that are not in the Haar random commutant will essentially be a probe of stabilizerness or magic in the other case. So we can use the commutant to construct kind of useful surrogates to detect magic. And then, of course, the key insight as well is that Cliffords have been used for random circuits and to produce K designs. So when it comes to, for instance, classical shadows, you want to have at least a 2 design, ideally a 4 design. And for randomized benchmarking, you want similar processes that you kind of are able to capture the entire unitary group, and this can be described with designs. And when you actually want to use that in practice, using Clifford is often nice because they are efficiently implementable and, of course, within the framework of error correction, quite useful. And then analyzing this design convergence, for instance, in a Clifford plus T model, you also need heavily this Clifford commutant. So I hope I motivated a bit why I find this thing interesting. Now I will quickly talk about the unitary group commutant, as I guess most people are familiar with it. So we again have basically we are interested in any operator that commutes with every tensor copy unitary. And as it turns out, these operators are only the permutations. So only those that swap copies around are the ones that also commute with all unitaries. Then we have these V pi's, which we can just write as as basically the swap operators on general permutations. And but for our purposes, because we want to characterize the Clifford group, and of course this is based on Pauli's, there's a different version of just writing the same objects using Pauli's. Essentially here we have just the swap operator, and this has this nice form in the Pauli basis that it is just the sum over all Pauli's tensor 2. That's just another way of writing a swap operator. And similarly, we can also then build products of these swap operators to get to arbitrary permutations. So on the left, we have, for instance, a cyclic permutation with 3 elements, and this is just the product of 2 swaps, so we can also write it in this form. Now, this unitary group commutant has a lot of nice properties. So first of all, since the basis that I just described to you is all swaps, they all are unitary themselves, and they all form a group. And this group is additionally, of course, a symmetric group, which has been well studied. One can use Young tuples to analyze it. And it also has, which is somewhat interesting, it also only has k factorial in many terms. So remember, we are considering different number of qubits, but actually the dimension of the commutant is independent of the number of qubits. So it doesn't increase when the number of qubits increases, which isn't true for most groups, but has an interesting property for the unitary group that also will be present for the Clifford group. So now it gets a bit more complicated. For the Clifford group commutant, we basically derive these omega operators, which form essentially the basis for the commutant. So these are kind of the generalizations of the permutations. They also contain the permutations, as basically since the Clifford group is a subgroup of the unitary group, the commutant of the Clifford group is just bigger, but also contains that of the unitary group. So what we have is, again, these products of Pauli's, tensors and power, and we sum over all of them. But additionally, we have this phase factor. This chi here is essentially pointing out whether the 2 Pauli's we sum over commute or don't commute. And then this matrix M gives us basically a phase. So we can add more signs into our descriptions, which weren't present in the unitary form. So the key relevance for this to form a basis is that we take these vectors V1 to Vm to be linearly independent on F2. And and these phases we can basically just consider kind of weighing different anti-commutation graphs of our operators. Now that just maybe as a brief motivation, why should those elements be in the commutant? So Cliffords map Pauli's to Pauli's. And what we are doing here is we are summing over all Pauli's. So what Cliffords then just do is they basically just rearrange the Pauli's, but this is invariant since we sum over all of them. We need that these tensor powers have even weight. And the reason for this is that Pauli's can also be mapped to minus the Pauli. So it would actually not be invariant if they have odd weight. And yes, and additionally, Cliffords can map Pauli's to Pauli's, but they need to preserve the anti-commutation relations. If 2 Pauli's commute before I apply a Clifford, then afterwards they would also commute. And therefore, we also have these invariant chi's essentially. Now, they have some nice properties, which they, of course, share with the unitaries as well, because with the permutations as well. First, they are quasi-orthogonal. So when we take the Hilbert-Schmidt inner product between these operators, they have d to the k as their overlap, which we just said. But if we take any 2 other elements, the overlap is suppressed in the dimension. This allows us, for instance, when we compute twirling operations to do a lot more. And they also, and that's a very important property, they factorize on qubits. So the number of qubits essentially doesn't really matter that much, because if we just have more qubits, we just need to tensor basically the single qubit form of those expressions to them. Yes, the annoying thing is a bit that the way we wrote them down, actually, they are not unique. We can essentially substitute Pauli's and get different representations for them, which is given by this gauge freedom. We work it out in the paper, but it gives kind of this ambiguity of these elements, which essentially means that this matrix V, which corresponds to these tensor powers, can be thought of as a binary vector space, essentially. We just have one representation of that vector space. So maybe some relevant terms. We have already seen these sums over P tensor V. So we call those primitive monomials if they only have one Pauli. And if the Hamming weight of these tensor powers is 2 mod 4, then we actually have unitaries. So these are unitary elements in a similar way as the swaps are. So for P tensor 2, this is a swap operator. For P tensor 6, we also have a unitary. So this is a unitary that's generally used when it comes for stabilizer testing, for instance. So you always essentially measure this operator in whatever form it is presented, but this is the operator. These unitaries then also form a nice subgroup of the commutant, and they have decently nice properties to analyze. But we also, on the other side, have these projectors, or stuff that is proportional to a projector. And these are when we have 0 mod 4 as our power. Here, essentially, when we compute the operator norm, this is exponentially big. So these operators are generally not measurable, and they are, of course, not invertible because they are projectors. So unlike in the unitary case, the Clifford commutant does not form a nice group, but only a semi-group, essentially, because we don't have inverses. But it's kind of relevant to classify them, for instance. So when we talk about state design convergence, we can essentially argue away the projectors. Effectively, because their operator norm is so big, their contribution to the state design is so negligible that we can just ignore it. We also, in the paper, developed kind of a graphical version of this, where we essentially just take this matrix V and write it as points, and this M as phase matrices between them. So this helps us to represent and analyze the structure. And just as an example, for instance, within like magic state resource theories, you often have these Bell sampling experiments. And there you have kind of terms people compute to show magic. And here, for instance, just from a recent paper, there's something that was defined as Bell magic. And we can actually use our formalism and our rewriting rules to show that this definition above, which is essentially using 2 Bell sampling experiments to compute some overlap over commuting Pauli's, can be rewritten in this form, where it's just essentially sums over Pauli's in our canonical form. Yes. Now, using those rewrite rules, we can also get to a simple form. Essentially, we can show that every monomial can be written as a product of primitives. So primitives, again, were just one single Pauli, and we can write everything as a product thereof. So this phase matrix M that I defined essentially is not useful, not necessary to generate the entire commutant. The reason why it is still relevant, essentially, is that the number of terms one might need to generate every element in the commutant, like this number L, can be bigger than the M of the definition. So the number of Pauli's we have in the definition and the number of Pauli's we need to kind of generate it multiplicatively can be different, which is essentially a bit tedious when we want to count them or characterize them. Then another property is that we can also separate the projective and the unitary part out. So we can write this every monomial as basically a projective part times a unitary part, which again is a nice characterization for these elements. And then we also show in the paper that actually this is still too much, so we don't need every primitive. We can essentially just use permutations, so the ones with Hamming weight 2, the projector with Hamming weight 4, and the unitary with Hamming weight 6 to generate the entire Clifford commutant, except for one special case where we need one extra element. So the logic is essentially that we have the unitary commutant, which is generated by permutations, and now we have these two extra elements that generate us the entire Clifford commutant. So we can use this essentially to classify all elements in the commutant. And as I mentioned before, so the main classification is basically are they unitary or projective. Again, for instance, when it comes to kind of magic state resource theories, we cannot measure the projective operators effectively. So if you want to detect non-stabilizerness, you need the unitaries. But there's also a second property that we can look at, and that is if we have permutations. So permutations acting on tensor copy states just act trivially, so they don't actually change our measurement result, which means essentially we can mod them out and only look at the ones which are not equivalent by permutations. And then this list of 11 operators is basically the entire commutant for k equal 8. And as one can see, most of those have some 0 mod 4 number of dots, so 4 or 8 dots, meaning that they all have a projective part and they're all not basically contributing to state designs. The only two that contribute is this omega 6 on the top and this omega 6,6, which is also equivalent to the spell magic quantity. So actually for small k, the size of the commutant, while being big, so if we add permutations, it's in the hundreds of thousands. If we analyze it structurally, it's actually not that many elements. Yes. Now, maybe just a quick way of how we can then also compute the basis. One aspect that's relevant here is that that these operators start becoming linear dependent if the number of qubits is actually too small. So they always span the commutant, but at some point they start having linear dependencies, which is essentially when the number of qubits is smaller than the number of copies. These dependencies we can analyze by going into a slightly different picture. So instead of summing over all Paulis, we now just sum over the Paulis that have a given anti-commutation graph. So we have the Paulis P1 to Pm, and we ask for them to follow a certain anti-commutation graph. Since the anti-commutation relations are again preserved under Clifford's, these operators actually also form a basis of the commutant. And if we additionally restrict that the Paulis are algebraically dependent, which for our purpose just means that they can't be products of each other, we get this basis, which has very nice properties. First of all, it is now fully orthogonal. So remember, the original basis was only approximately orthogonal, having kind of the suppression in the Hilbert space dimension. Now they are fully orthogonal. And additionally, we can see when the dimension gets smaller. So if we make n smaller, the reason why the dimension of the commutant decreases is because there just doesn't exist a set of Paulis that satisfy a given anti-commutation graph. So for instance, if the anti-commutation graph is empty, so all Paulis need to commute, we know that on n qubits you can at most have n stabilizers. So if m was n plus 1, then this just would vanish to be the 0 operator, and thus of course not contribute to the dimension. Yes, so this gives us a definition or like a condition for when these operators contribute, and therefore we can also explicitly count the number of the dimension of the commutant. So we have the sum m, which just counts how many products of these Paulis we had in our definition. And then we have the contribution of the V term, which is the binary vector spaces. And then we have the contribution of the graphs. And here the graph contribution actually, the question of if a given anti-commutation graph is possible on n qubits can be related to the rank on F2 of the adjacency matrix of the graph. So we actually have this condition that the rank of G is bigger than 2 times m minus n, so that there actually exist Paulis that satisfy this condition. Now, if we plug all of this in, so all those functions essentially have been computed already, we can exactly compute the dimension for every n and k. And in general, basically, if if 2n is bigger than k, then we have a constant size of the commutant and everything is linear independent. But if the number of qubits gets smaller, then actually also the size of the commutant gets smaller. And now it behaves like 4 to the kn minus n squared. Remember, 4 to the nk is also the number of operators we would have in the entire space. So the size of the commutant is, as one might expect, very big in comparison. Yes, so some further results we have. So in our paper, we also extend everything to qubits. There, the formalism essentially becomes a bit more complicated. We now have finite fields, not just binary vector spaces. We also talk about the measurability of these operators via Bell sampling. So quite a few of them have already been kind of studied within that context, and we find sufficient conditions for when these operators can be measured in experiment. And we also then define basically magic state resource theories based on these operators to classify non-stabilizerness. And yeah, we also, so now I just described the commutant. When you work with it, you essentially need to compute overlaps and you need to invert some Gram matrices, which is fancily called Clifford-Weingarten calculus. So we also work this out and give asymptotics and tools to use it. Yes, then in future work, so these tools we believe can help us to develop better kind of unitary design convergencies and also better convergencies for stabilizer states as well as conditions there. And another interesting aspect is that actually these operators have an interesting extension if we allow for partial transposes of the subsystems. And that is surprisingly the same as if we would look at the commutant of only the real Cliffords. So only Cliffords that have a real orthogonal matrix representation. And yeah, so this connection I think is quite interesting, and we will be working that one out as well. Yeah, so in conclusion, we essentially describe the commutant. We show a small set of generators are sufficient. We show how to manipulate it, how to understand it a bit, how to count all dimensions and properties and their relationships, as well as yeah, how to perform twirling operations. Cool. And with that, I thank you for your attention. And
questions? The session is open for questions. So any questions?
Thanks for the nice talk. So I was wondering that given that there is already like many applications of a similar type of results, do you envision that this theory that you have developed can have any kind of algorithmic application?
Algorithmic in the sense of the examples that I gave, or
a new application, like these new results might lead to a new algorithm to do a computational task.
yes. So so we already have one paper where we talk about, so there exist these kind of measures of magic, for instance, and we have one result which can directly, using this technique, we can show that that essentially if this measure is high, then if we take the state and we Clifford twirl it, it actually forms a state design. And the reason for that is to understand it. So this was kind of the main motivation for why we looked further into it. Yeah. Another aspect is that in like previous papers, this number m, so this number of Paulis, is not that present. They essentially looked at it from a different perspective. So they didn't have this number m. But this is actually quite crucial when we kind of want to characterize the number of terms. So essentially, when, for instance, for this point, so there exists kind of this quantum homeopathy paper about using Cliffords and T-gates to generate designs. And there, our techniques, because we kind of have a better coarse-grained structure, can improve the overall scaling in T and the quality of it.